Okay, in this video I'm going to show you how we can use the idea of a flux graph to determine what the EMF is doing through a coil in a range of situations. And to exemplify this, I'm creating a problem where we've got a single coil and we're going to drop a magnet through the loop of the coil. And what we want to do, we want to find out what will the graph of the EMF of this coil look like as this magnet falls through the loop. So, we've got a loop of wire, as I said, and our magnet has a north pole, and let me just change that. Yeah, that's okay. So, our magnet has a north pole, and that's the south pole there. So the north pole is going to be there. Okay, so there's our magnet, and our magnet is falling downward through the loop. So it's going to fall through that loop and just keep on falling. Now, what we want to do, we want to generate some graphs to see if we can get a picture of what the EMF is going to look like. So, let's assume, firstly, that to keep things a little bit simpler, we're going to assume it's moving with a constant speed, okay? So I did say falling, but I think if it's going to accelerate, that could add a layer of complexity which we perhaps don't need to look at just yet. So we've just got a magnet that's falling at a constant speed through a loop. Now let's draw in our field lines. Now I hope that you can actually do this on your own. So have a go and see what you can do on your own. Okay, welcome back if you happen to pause it. Drawing the magnetic field of this bar magnet, remember, the field lines go into the south pole. So the field lines are going to look like this. And they're going to be emerging from the north pole like this. And so, of course, each of those lines goes around and connects with the other end of its arrow. So they are complete loops. Okay, so remember, they are all complete loops. So each of those lines passes through the bar magnet, and this is important for this problem. And so each of those form a loop around like that and connect around like that. Okay. So what we want to do, we want to see what the EMF looks like through this coil as the magnet passes through. But before we can actually get a handle on what the EMF looks like, we need to know what the flux is doing. So if we can get a picture of what the flux is doing over time, that will allow us to look at what the EMF is going to do using the same three graphs that we used in our lesson on EMF and flux graphs. By the way, remember, each of these graphs is plotted against time. Now, it's probably useful in this situation to break this scenario into three different periods, because there's three different things happening here, or there's three different zones, if you like. There's the magnet approaching the coil, then the magnet penetrates the coil, and then once the magnet passes through the other end, it then falls away from the coil. So what we can do is perhaps just label those using, I don't know why that happens. Okay, and I'll draw another zone there. Okay, So these are our three zones. In zone A, we've got zone B and zone C. In zone A, the magnet is approaching the coil. So that's the approach. In zone B, the magnet, the south pole of the magnet, the tip of the magnet has penetrated the surface, if you like, or the plane of the coil, and so the magnet is now threading the coil. So in zone B, the magnet has threaded the coil. In zone C, the north pole of the magnet has just exited the coil, and so it is now leaving the coil. It's now moving away from the coil. Okay, so it might make sense then if we look at these zones one by one. So, in zone A, what's the flux going to be doing? Well, the magnet's going to be moving closer to the coil, which means more of these field lines are going to pass through the coil. As the magnet gets closer to the coil, more of these lines are going to thread the coil. So our flux is going to increase in that direction. Okay, so we're going to get an increase in flux. And let's say then that as it approaches, the flux is going to increase in a linear fashion. So, ruler. So, in zone A, what we're saying is that the flux is increasing as it approaches the coil. So we'll do that in white. So there's the flux. Pardon me. Okay, so here's our flux increasing. Now, once the magnet has penetrated the coil, the flux remains constant. So whilst the magnet is in the coil, whilst the magnet is through the coil like that, the flux through the coil is constant. And the reason is, if you remember, every single field line that is emanating from the magnet and going around, going back in the south, every single line passes through the bar of the magnet, linking the south and north pole. Which means when the magnet is threading the coil, every single field line is passing through the magnet. Not through the gap here, but through the magnet. Now whether the magnet is here, or whether the magnet has dropped down a bit and it's further down like that, every single field line is passing through the coil. Therefore, the flux is not changing as the magnet penetrates the coil. So in section B, the flux has reached a maximum but remains constant. So in section B, as the magnet falls through the coil, because every single field line is passing through the coil, the flux stays at that maximum value. Now, as the magnet now leaves the coil, the strength of the magnet, the field lines of the magnet are getting less and less and less as the magnet moves further and further away. And so the flux is now going to decrease, and at the same rate that it increased at, because remember, it's a constant velocity. So now, as the magnet recedes from the coil and leaves the coil, it falls away, it's going to reduce back down to eventually zero. So the graph will look something like this. So there's the graph of our flux. As it approaches the coil, it increases. Then, as the magnet threads through the coil, it's constant. And as it falls away the other side, it reduces again. Now remember, the EMF is related to the negative rate of change of flux. So the next thing we need to do is look at the gradient of this graph. Well, in section B, that's easy, isn't it? The gradient is 0. So gradient is 0 there. In this section, the gradient is positive and constant. So it's a constant gradient, which means if we're going to graph our gradient here, that's the rate of change. Oops. That's the change in flux over the change in time. So it's going to be a constant positive value. So it'll be some constant positive value. In section C, the graph is a constant. The gradient is constant but negative. So it's going to be something like this. Let's link up our sections. So section A, we've got a positive change in the flux. In section B, we have no change in the flux. And in section C, we now have a decreasing change in the flux. So remember what we said, the EMF is related to the negative rate of change of flux. So here's our rate of change of flux. So all we need to do now is make this negative or invert this. So the actual graph of the EMF will be, I won't use my ruler just to save time. So there's the graph of our EMF. And note that for the time that the magnet was threading through the coil, there is no voltage. Why? Because there's no change in the flux. So that's an example of how we can use the idea of these three graphs. Given a scenario like this, if you can work out what the flux is doing, you can then work out what the EMF is doing in that coil. And so if it took 3 seconds for the magnet to reach from here, from the end of the magnet to reach from here to the edge of the coil, that would be that 3 seconds there. And if it took another 1 second for the magnet to pass through the coil, then that would be 4 seconds, not drawn to scale, of course. And for that, so for that intervening second in there, there would be no voltage created. Okay, that concludes this lesson.